You can see my slides?
Yes, sir. Yes.
But
good morning, sir. Abhishek, sir.
good morning.
Dr. Sachin Ambade here.
Okay.
Am I audible to you, sir?
Yes. Yes, sir.
So wait for some time.
Yeah.
Because
I'm just checking.
audience is joining now.
Okay.
For me, people join. Okay, good morning, everyone. I'm Dr. Sachin Ambade. It's a great pleasure. Yes. Any problem to anyone? Okay, it's a great pleasure for me to introduce our today's guest, Dr. Abhishek Sharma, who is going to talk on friction stir welding. I'm giving a brief introductions about him. Dr. Abhishek Sharma has completed B from Government Engineering College, Vidisha, MTech from NIFT, National Institute of Foundry and Technology, Ranchi. Then he has completed his PhD from one of the reputed college, IIT, Indian Institute of Technology, Kharagpur. Now talking about his research, he has published 25 paper in referred journals and 6 paper in referred conferences. He has a big achievement is he has published a paper in Journal of Carbon. The impact factor of that journal is more than 9, and remaining paper he has published more than 5 impact factors such as Journal of Material Process and Technology, Carbon Letters, Material and Design and Material and Design, Manufacturing Process. These are the big journals. He is having 535 citation in Google Scholar. He has worked as a reviewer for the several SCI Index journals, and he is a guest editor in MDPI journal. Currently, he is working as a researcher in Joining and Welding Research Institute, Osaka University, Osaka, Japan. Now, I'm inviting our today's speaker, Dr. Abhishek Sharma, to share his immense knowledge with us. Sir, over to you, sir.
Oh, okay. Thank you, Dr. Ambade, for such a nice introduction. Okay, so I'm Dr. Abhishek Sharma, and today I will be talking about my research area, that is friction stir alloys, alloying and processing of aluminum alloys. Okay, so the content of this presentation will be as follows. Like in the initial, I'll be discussing the basics of friction stir alloying and processing and what are the differences and other variants of friction stir welding. Then I will be covering my two present topics, projects on which I am working right now. That is the through thickness friction stir alloying of ALFE alloy system, and another one is where we have combined spark plasma sintering with friction stir processing for pure aluminum alloy. And in the lastly, I will be discussing some other allied processes of frictional stir welding related with the frictional stir welding. Okay, so now there are many processes which have emerged recently based on the principles of frictional stir welding. Like the frictional stir welding is the initial one, and it is mainly used for the butt welding and lap configurations, as well as in the underwater welding and spot welding. It is primarily used for aluminum alloys, and mainly it has applications in the aircraft industry right now, as well as in the bullet trains, high-speed vehicles. The another variant of the friction stir is alloying, where the local modification is carried out by reinforcing some other elements on the base metal. And one such variant is processing, where instead of another metal, some other reinforcements like silicon carbide or graphite is being added to the base material to enhance the surface properties. And the most important one is the additive manufacturing, which is recently developed, where the layer by layer deposition takes place uh, to construct a product in a 3D model. And the other variants are like cladding, where another metal is joined over one metal to provide resistance from corrosion or wear such properties. And one more is the channeling, where a channel is created by the solid state in a solid state welding through solid state, and extrusion and brazing are also the similar process. So in this presentation, I will be discussing mainly on concentrating on four processes, that is alloying, processing, and we'll be just a brief introduction about the additive manufacturing and the frictional stir channeling. Okay, so coming to my first uh, presentation topic, that is the introduction. Now, what is frictional stir alloying and processing? So this is a solid state process. It consists of it is a variant of one of the important variant of friction stir welding, and it consists of a base material. And in this base material, we create one groove, and the reinforcement is filled in this groove. And later, there's a non-consumable tool which has two types of motion, that is a linear motion and a rotatory motion, which is, and the tool moves in close contact with the surface. So the frictional heat is generated by the heat is generated by the frictional interaction between the tool shoulder and the base material, and as well as the plastic deformation which is carried out in a solid state. It is responsible for the heat. And in this way, the localized heating is generated, which softens the material around the tool pin, and this rotatory motion makes the material flow. And in this way, this reinforcement material, whichever in the groove, is getting filled with the mixes with the base material. And in this way, the alloy or composite based on the reinforcement is produced in the solid state. Now, based on the reinforcement, if the reinforcement is another metal, suppose if a base metal is aluminum and the reinforcement is like copper or iron or magnesium, anything, then we can say this process is alloying, that is friction stir alloying. There's no reinforcement, or if there is another reinforcement which is non-metallic like silicon carbide, graphite, tungsten boride or tungsten carbide, etc. These are then the process is termed as usually termed as friction stir processing. However, the basic principle of both the processes is same. Now, why we are conducting this processing in a solid state when we can do it in casting? Because certain advantages of this process, that is the microstructure can be easily controlled. The whatever is producing, we are producing it in a solid state, so the material properties remain intact. The overall material setup cost is very low. It can be done on a milling machine, and The particle impregnation depth can be easily controlled by the tool pin. This is a tool and it is having a pin which is inserted into the base material. So by controlling the pin depth or the pin height, we can easily control the depth of particle impregnation. The process is green and energy efficient as it does not involve any slurry or it does not involve any shielding gases, fumes, etc. And this is a one-step solid-state processing for the microstructural refinement. The grains obtained after friction stir processing is very fine. And densification, there is no defects like porosity or gas shrinkage or anything. And the particle dispersion is mostly homogeneous across the thickness, across the shoulder or the processing zone. Now coming to the first project that I'm working here, that is the through thickness inhomogeneity in the friction stir alloy ALFE alloy system. Now after thinking of the title, the question arises why ALFE alloy system? Because in ALFE alloy system, when it is fabricated by friction stir alloying, there is a generation of plastic strain and exothermic reactions. These exothermic reaction and plastic strain leads to the formation of Al13 Fe4 intermetallic layers. This intermetallic layer, when reinforced in the aluminum, it increases the tensile strength, it improves the hardness as well as it improves the corrosion resistance. Now again the second question arises, why only Al13 Fe4 and not another other type of IMCs? So based on the effective heat of energy formation of the ALFE binary phase diagram, there are four possible intermetallic phases can be formed by the reaction of aluminum and iron. So based on that, AL5, Fe2 and Al3Fe, which is also known as Al13Fe4, they have the least more negative heat of energy formation. So the chances of forming these intermetallics are more as compared to the other iron-rich intermetallics. So these are the red one which is shown here. These are the aluminum-rich intermetallic compounds, and they enhances the properties. They are hard, brittle substances which are impregnating into the aluminum surface. So it is increasing the hardness, tensile strength, etc. Now the another question, why through thickness and what does it means? Through thickness means when in the friction stir welding, when we are doing the shoulder, the heat generation is not homogeneous. On the top of the surface where the shoulder is interacting with the base plate, the maximum heat is generated. And when we move across the thickness, the heat generation changes, the temperature varies, and similarly the strain and the residual stresses varies. So based on these
हेलो सर, मैं कनेक्ट
parameters,
नहीं हो रहा सर.
any problem? Is there any problem?
No problem, sir. You may
Okay.
start.
Okay, so based on these parameters, since these parameters vary across the thickness, so the particle dispersion varies, and there is an inhomogeneity exists in the material across the thickness. So we need to understand these heterogeneous dispersion and what is the variation, what are their effects on the properties. So that's why we have conducted. This is the schematic of the through thickness experiment. This is a base plate, aluminum, and this is a groove where we have filled the iron powder. And this is a tool, a non-consumable tool. It is having a linear as well as the rotational motion, and it is moving over the groove filled with iron. And this is the formed zone, the alloyed zone. And we have extracted the samples from the stir zone. And we have further sliced the sample into three parts, that is top, middle and bottom layer. And you can see the cross-sectional schematic here. So this is the top layer, which starts at the top and ends at 2 millimeter. And then it's a middle layer and then it's a bottom layer. We have observed a bimodal distribution of particles in the particles as well as the grains in the upper and bottom part of the upper and bottom lower part of the bottom layer. So we have further classified into its upper bottom and the lower bottom section. And here we have used the shoulder diameter of 18 millimeter. It means the processing zone is 18 millimeter, and the particles are mainly reinforced in the zone of 6 millimeter because it's a pin diameter. So we call it as a stir zone. And the parameters which we have used is 1500 RPM, tool rotational speed, and 200 millimeter per minute. And we have carried out the number of passes, that is 3 with 100% overlap. And you can see the samples which is formed here. And we have sliced the sample tensile specimen into 3 parts, 3 layers, which can be shown here. Now coming to the particle dispersion microstructure, this is the cross-section micrograph. So this black part can be identified as the iron-rich zone, and this is a fully etched micrograph. So a very well stir zone and other zones can be classified. Now the two interesting features which are observed from here is that this is the advancing side and this is the retreating side. So the particles are mostly dispersed on the advancing side instead of the retreating side. And this happens only in the top layer, because in the top layer, there's a shear zone is formed around the pin. This shear zone is very dominant in the top section, which throws out the particles from the stir zone to the advancing side. Now, why only advancing side, not on the retreating side? Because the material movement is from the retreating side to AS at the tool rear, which causes the dominant dispersion on the advancing side as compared to the retreating side. Whereas in the middle and the bottom layer, this shear zone is very less dominant, and it does not significantly affect the particle dispersion, and that's why the particles remains mostly in the stir zone only. Now we have also observed this is the high magnification SEM micrograph. We can see that in the middle region, these white particles are the iron particles. These are homogeneously dispersed, and this is the bottom region. So in the bottom region, as I said, there's the bimodal distribution. So we can see that in the upper bottom section, the particles are some particles can be seen, whereas in the lower bottom section, there is no particle. So it means that this is the iron deficient region and this is the iron rich region. Okay, so interestingly, we have observed that the particles can be impregnated up to 4.9 millimeter depth. The last particle which is impregnated is at 4.9 millimeter. And yeah, luckily we have a pin length of also around 5 millimeters. So we can see that the first benefit, that the particle impregnation depth can be controlled by the pin height, which is achieved here, and the particles are impregnated up to a pin height only. And there's a homogeneous dispersion in the middle and a bimodal distribution in the bottom section, as explained earlier. We have also conducted some high magnification SEM micrography to evaluate the nature of particle dispersion. And this is the advancing side on the top. We can see that there are some agglomerates of the particle. These agglomerates can also be visualized in some high magnification micrograph here, whereas in the bottom, in the middle and in the bottom section, the particles are homogeneously distributed. Now the interesting thing is that the particles in the top region, they don't have a well-defined shell intermetallic layer as can be seen here. This is only for very few particles we have observed. However, it is around 7 micrometer thick, whereas in the middle and the bottom, the most of the particles have a IMC layer around them. So these particles, however, the thickness is around 3 micron in the middle and the bottom section. Now the reason behind is that in the top region, the particles, the shear stresses are the shear stresses are higher, so which leads to the fragmentation of this layered structure, and that's why the particles are not this layer is not visualized. However, the fragmented particles of this IMC layer is visualized. This is the IMC layer which I'm talking about, and this is the Fe particle. And we have observed a different variation in the color contrast. The black part is the aluminium, the gray one is the IMC layer, and the white bright one is the iron particles. So this is the reason for this distribution. We have further classified this IMC layer through electric dispersive spectroscopy, and we have identified this composition of this IMC layer is equivalent to that of Al13Fe4 IMC layer, IMC particle. Now as I said, discussed this earlier, that the stress zone of the top section is particle deficient and iron particles are agglomerated on the advancing side only. And there is a continuous disruption and formation because in the top section, the temperature is also higher for the diffusion of iron atoms into aluminum. So the reaction is also higher. So the chances of formation of IMC is also more prevalent in the top section, but simultaneously the stirring action is also more dominant. So that's why the disruption of this layer also takes place simultaneously with the dominant disruption. And the middle section is the most efficient dispersion we have observed. Now coming to the high magnification transmission electron microscopy, we have obtained a sample from the stress zone. As already said in the top section, the stress zone of top section is a particle deficient region. So there are no iron for the diffusion or the reaction with aluminum. So that's why we have observed only very few particles of IMC layer is observed here. And this is a well-defined elliptical shape IMC Al13I4 IMC particle. And on side indexing, we have confirmed this particle as the IMC particle, and also the ADS analysis further confirms it. The middle section of the ALF alloy shows very interesting feature. First of all, there's a homogeneous dispersion of particle as can be seen with the ADS mapping here. And the other features is there are two types of IMC particles can be observed here. The first one is the elliptical one. This is the ellipse-shaped particle which we have observed. The others are the irregular ones. This is the irregular shaped IMC particle. Now, why these two types of morphology we have observed when the reaction is one? So this is the by TEM analysis we have identified that region is that this elliptical shaped particles are precipitated out of the matrix, whereas these irregular shaped, these are the fragmented particles from the layers formed around the Fe particle. So that's why these two types of morphologies are visualized. Now the interesting thing is that the elliptical shaped particles, they are very small, so they can contribute in the grain pinning mechanism or the Hall patch mechanism to restrict the grain formation, grain growth. Whereas these large particles, they helps in particle stimulation nucleation. They provide the sites for the heterogeneous nucleation in the solid state for the grain. So in these two ways, these contribute in the grain refinement. The another feature is that this is the IMC particle and it shows some nano twins. Now, what is the nano twins? These are the defect structures in the IMC particle. And what happens is that when the dislocation tries to move across this particle, these nano twins provides a blockade, and due to this blockade, the dislocation is forced to have a bow motion instead of shearing motion. So the particles cannot be sheared easily, and that's why they provide a precipitation strengthening. Another interesting feature is the incoherent interface, as can be seen here. This is an incoherent interface, so the dislocation movement is further restricted by this incoherent interface, as it is having a higher energy. These are the high energy interface. So based on this features, we can say that the strengthening is provided in multiple ways by the IMC particles in the aluminum matrix. So here I have discussed the uniform dispersion of IMC particles, the incoherent interface, the nano twins which are formed, and the defect structure on IMC particles. We have observed that these small shapes, hole morphology, these are the defects. But when we have done the high magnification microscope analysis, we can say that these are not the holes, but instead these are some cavities. And when there is a localized melting of aluminum, this aluminum deposited in these cavities and then solidified. So these are the aluminum rich zones instead of we can say that they are the hole defect in the IMC particles. Now, as I said, these small size IMC particles contribute in the grain boundary pinning, as can be seen here, and also here. The grain boundary pinning and the dislocation blockade can also be visualized here. The PSN mechanism by unreacted Fe particles, which is also visualized in some of the cases. Now, from the bottom section, in the bottom section of the ALFE alloy, the heat available for the diffusion of iron atoms and the aluminum, it is very significantly low, and there is no such reactions. However, there is reaction, but it is very less dominant as compared to the top and the middle section. So we have found the unreacted Fe particles here. So further said, and this is confirmed, these particles are the SAT particle the unreacted Fe particles. And however, we have observed a layer also. This is a diffusion layer or the IMC layer which is formed around the Fe particles. But this layer is having such a high thickness because in the bottom part the stirring action is also very less. So that's why this is not broken and this is not fragmented and it remains intact with the particle. So here we can see that some of the IMC particles which are precipitated and formed in the matrix. So here also like two types of morphology is obtained. The one is the irregular one and another one is the ellipse-shaped morphology. Now coming to the microstructural evaluation, this is the microstructure of the base material. We can see the elongated grains, which is a typical rolled structure. And this is the microstructure of the top region.
वरती काय म्यूट आहे की अनम्यूट ऑप्शन आहे अनम्यूट साइड आहे
This is a microstructure at the top, and these are the microstructure at the bottom and the upper lower section, and this is at the bottom lower section. So we can see that at the top. Any problem?
No problem, sir. You can continue.
Okay, so we can see that at the top, the temperature is very high, which results in the grain growth, whereas in the bottom and the upper lower section, the temperature is not significantly high. So that's why, and also the IMC particle with multiple mechanisms restrict the grain growth. And so we can see that the grain size is very fine here, around 3.6 micron. And in the bottom part, we have observed around 5.2 micron grain size. In the lower bottom, the microstructure is resembles to that of the base material, and the grain size is around 14 micron. However, these grains are recrystallized and they are equiaxed grains, we can see. And coming to the tensile properties, we can see that the middle section has the highest tensile strength as compared to the bottom and the middle one. The bottom section has the highest tensile strength. Now why? Because of the bimodal distribution, the fine grain size provides the strength, whereas the big grain size, the large grain size, it helps in the dislocation accumulation and thereby provides the strain or the higher elongation as compared to the other one. And also in the stir zone, since the particle dispersion is homogeneous as we have seen, so the higher and homogeneous hardness is obtained. Whereas in the advancing side, the top section, the particles are dominant on the advancing side. That's why the higher hardness on the advancing side is obtained. Now coming to the reaction. So this is a Fe particle and this is aluminum. So what happens where the diffusion of iron and aluminum, Al13Fe4 layer is formed here. And since these are the rates of diffusion of iron and aluminum in Al13Fe4 IMC layer, there will be a unidirectional diffusion of iron atoms into this layer, and what happens, the content of Fe keeps on increasing. So this provides the foundation for the reaction of Al5Fe2. However, in our case, as soon as this layer is formed, Al13Fe4, by the stirring action, it is removed from the Fe particle. And that's why there is no foundation for the formation of Al5Fe2. And thus we have avoided this brittle intermetallic particle from our structure. Coming to the conclusion of this talk, this part of the presentation, we have obtained the through thickness inhomogeneity in the middle section, and middle section is the best section, and it is having a highest strength. The two types of morphologies are found, that is elliptical shaped and irregular morphology. and the finest grain size was obtained in the middle region. Now coming to second part of the presentation, that is this is my project, second project, where we have combined the spark plasma sintering and frictional stir processing. Now why we are combining these two advanced manufacturing strategies? The reason is that the spark plasma sintering, when the powdered billet is formed with SPS, it has some porosity. However, it is 95% dense, but still there are 5 to 10% chances of porosity. This porosity have reduces the density of the component and the hardness as well as the tensile strength. Another problem with the spark plasma sintering is that the grain size is very high because of the long exposure to the higher temperature. So the grain size is very high. So due to this higher grain size, again further reduces the tensile strength. So the solution, which is the most prevalent solution, is to subject these powder metallurgy components to some kind of severe plastic deformation process like rolling or extrusion. So what happens with the rolling? When we do the rolling, the density is 100%, but again the ductility is reduced, and the microstructure consists of low angle grain boundaries fraction, high fraction of low angle grain boundaries. So the ductility is severely compromised. So we came up with a solution that to combine the spark plasma sintering with the friction stir processing for it. So in the first step we have done the spark plasma sintering, and we obtained a powder billet with a 30 millimeter diameter and 5 millimeter thickness. And these are the process parameters we have used. We have the most important parameters are like the temperature is around 550 degrees centigrade and sintering time is around 20 minutes. And we have produced this billet. In the second step, we have done the cross rolling. What is cross rolling? The cross rolling, it means the specimen is rotated by 90 degree after each pass. So first pass we have obtained on the billet of dimension like around 32 millimeter width and on the minor axis, and the major axis has around 55 millimeter, which is further in the second pass it is rotated and again passed through the rolls, and then we obtained around 40 millimeter diameter and 2.5 millimeter thickness. So it is a 25% reduction in each pass we have obtained. Now the primary reason for doing the cross rolling is because we have to fix it on a FSP FSW setup. So this fixing of this setup is difficult from our end, from the machine which is available here. So that's why we transformed it into a circular geometry and for the fixing purposes. And in the third step, we have done the friction stir processing. Now, friction stir processing, as it involves, this is a pure aluminum billet formed by the spark plasma sintering, and we have done the processing at anywhere in the with the two passes, and we obtained a tensile specimen such that the whole processing zone comes under the gauge length. And we have done the use the process parameters like 1000 RPM, and we have done a traverse speed of 50 millimeter per minute. We want to use this technique for graphene and carbon nanotube composite. So that's why we keep the temperature such that there will be a minimum heat input in the system, so that there is no interfacial reactions between the carbon and like graphene and CNT to form the aluminum carbide, because this aluminum carbide reduces the strength of the material. So that's why we designed the experiment in such a way that the heat input, the overall heat input is very less in the system. So we have done the FSP with two passes. However, we are still optimizing this process, and we are further increasing the number of passes to 3 or 4 or some where we can obtain the optimized properties. And we have done it with 100% overlap. And this is the final product that we have obtained. This is a billet, and we have done a nice friction stir processing over it with a very fine dimensional tolerance. So in this study, I will be abbreviating the compared. We have compared the specimen with the annealing, because annealing is the most prominent heat treatment given to restore the microstructure loss by the or the ductility loss by the rolling. So we have annealed the specimen to compare the effect of friction stir processing with that of annealing also. Now coming to the microstructural evaluation, we can see that this is the spark plasma sintered billet. The grains are equiexed and recrystallized grains. Very fine grain structure is obtained here, which is around 17 micron. And on rolling, the microstructure transforms and there are low angle grain boundaries can be formed. And this is a typical elongated grains, which we can see here. And the grain size reduced to around 7 micron because of the subgrain structure formation. And on annealing, the typical recovered structure can be seen where the low angle grain boundary fraction is reduced, and however the grain size is almost same or increased because of the exposure to the high heat around 13 micron. On FSP, the fine aqueous grain structure is formed, and this structure is completely different from all these three because of very fine structure. However, the most interesting thing is that it has around more than 77% high angle grain boundaries. It means these fine structures, they are not subgrains. Instead, they are grains. So we can confirm with this surety, we can say that there's mechanism like discontinuous dynamic recrystallization mechanism for the formation of these fine grains. Another statement which supports another proof which supports this statement of dynamic recrystallization, because it rarely happens in the aluminium. Aluminium is mostly recovered, mostly shows the recovery and not the dynamic recrystallization. The recovery and the CDRX are the most prominent recrystallization mechanism in aluminium and not the dynamic recrystallization. But here we can see that the 25% grains are of nano size. This nano size grains, it is and this with this high angle grain boundaries, this fraction of HAGB, it is difficult to form by the continuous dynamic recrystallization. So we can definitely say that the discontinuous dynamic recrystallization occurred here. And coming to the TEM microscope, we have further confirmed that this is the rolled specimen. ABC are for rolled specimen and DEF are for the friction stir processed specimen. And we can see that in the rolled specimen, the grains are very large and it has various features like subgrain formation, dislocation, cell dislocation, tangles, etc. And it shows a typical recrystallized structure by the formation of subgrains. And in the FSP structure, a recrystallized micro with equiexed grains can be visualized here. The most of the boundaries are, we can see that these are the boundaries with the high angle grain boundaries with sharp and clear features. And the interesting thing is that in the rolled specimen, we have observed the continuous dynamic recrystallization. Here we can see that the dislocations are coming and absorbed at the geometrical necessary boundaries, and with the random incidental dislocation boundaries, which is trapped under the geometrical necessary boundaries. So we can see that the continuous dynamic recrystallization occurred in the rolled specimen, and whereas in the dynamic recrystallization, discontinuous dynamic recrystallization occurred in the FSP structure. Coming to the mechanical properties, we have observed that the rolled specimen shows the very less ductility with the higher strength, whereas the spark plasma sintered specimen, because of its large grain size, it shows the higher elongation, but the strength is very less. So what we say, an intermediate properties is described in the SRF specimen, which the sufficient ductility as well as the higher strength. And we can say that the minimum yield strength and maximum elongation is obtained by spark plasma sintering, but with the rolling, we can the maximum yield strength and minimum elongation. So a balanced strength and ductility combination is achieved in SRF.
ट्रांसफर हो जाता है इसलिए नहीं है, मैं ज्यादा लोगों को नहीं बताया इसको बताया तो ये मात्र से डील द्वारा बिटता है इसलिए तो मैं बस तेरे को
Sindre, unmute your mic.
Okay, so we can see we have calculated the theoretical strength, and we can see that the dislocation strengthening is the primary strengthening mechanism in the rolled specimen, whereas in the FSP specimen and FSPD specimen, the grain boundary strengthening is the prominent strengthening mechanism. We have compared our results with the existing results, and we can say that the strength ductility combination is achieved here. Better strength ductility combination is achieved here. Now coming to some other allied processes, we have friction stir additive manufacturing. Now what is friction stir additive manufacturing? It consists of a base plate, and there's a tool which is having a filler material, and this tool is moving over a substrate material, and within a solid state a layer.
शर्मा सरांना सांगा एकदा अनम्यूट करा.
Hello, sir. Sharma sir, please unmute your mic, sir. We can't hear you. Sir, am I audible? Sharma sir?
Yes.
Please unmute your mic, sir. Yes.
Okay.
Yes. We are audible, sir.
Okay, fine. Okay, so this is a additive manufacturing and friction stir additive manufacturing. Here it consists of a plate, and we keep another plate over it, and we do the friction stir processing. And in this way, that layer by layer, it is joined. And the advantages of this process is that it makes a object in the 3D model, and there's a strong bonding, no hard cracking, and it avoids residual stresses. And there's an intensive material flow. And another variant is that the friction stress channeling. So we can see that a solid tool is moved over this plate, and in this fashion, and the material is removed from the base plate by the extrusion process, and in this way the channel is formed. So we can flow one liquid from this end, and we can obtain it from this end. And so it is used for mainly for the electric vehicle battery trays and cooling in electric motor casings, jet engines, etc. Okay, so with this slide, I will like to conclude my presentation. Thank you.
Thank you, Dr. Abhishek Sharma, sir. Thank you very much, sir, for giving your immense knowledge about friction stir welding, sir. Thank you, sir.
Thank you.
आप लैपटॉप लेके इधर पर बैठ जाना, इधर कोई भी लैपटॉप लेके.
Anybody would like to ask questions? Any participant, anybody would like to ask any question to Dr. Abhishek?
Hi.
Anyone from audience? Unmute.
Sir, I have one question.
Yes,
Okay.
yes.
Sir, why you choose Japan for your research work?
This is totally out of the league question from the presentation. I was expecting
questions must be related to the presentation and technical contents. It should not be out of league questions. You are requested to please stick to the technical contents. If you have any questions related to the technical aspects, you can ask Dr. Abhishek.
Anyone having some questions regarding the research
No,
work,
sir.
regarding the friction stir welding?
So it seems nobody is having questions. Dr. Abhishek, thank you very much.
Thank you.
It's my pleasure and sincere gratitude and thanks for delivering a keynote address for our department, for accepting our invitation. This is Jayan Giri from Department of Mechanical Engineering.
Okay.
Thank you very much. In the nearest future, we are looking forward for association with you in terms of maybe a guest lecture for our students, maybe in terms
Yes,
of some research ideas or something like this.
Yes,
So
sure.
thank you for sparing your valuable time with us, sir.
Thank you. Thank you, sir. Thank you for providing this opportunity.
Thank you. Thank you.